Hello everyone. In this video, we would be discussing the questions of the Chemistry Paper 1 of IBHL 2020. This video is specifically made for the first 20 questions, that is from question 1 to question 20 only. And in the next video, we would be covering from question 21 to question 40. So let's start with the first question. So in this question, you are asked to calculate the total number of carbon atoms in 12 grams of ethanoic acid. Okay. Now, to do this question, to solve this question, firstly, we need to know that we have two atoms of carbon. We have two atoms of carbon in one molecule of CH3 COOH. Okay, so I can extend it and I can write that there are 2 moles of carbon in 1 mole of ethanoic acid. Now, firstly, let's calculate. So this is the first step in solving this problem. Okay, in the next step, let's calculate the moles of ethanoic acid. Okay, so NCH3 COOH. This would be equal to your 12 grams is the given weight divided by the molar mass. It is 60 grams per mole. So what we get here is 1 by 5 moles. Okay. Now we know that in 1 mole of ethanoic acid we have 2 moles of carbon. So in 1 by 5 moles, obviously you will have 2 times of the moles of ethanoic acid as the moles of carbon. That is 2 times 1 by 5. That is 2 by 5. So finally, when we are calculating number of atoms, it would just be the moles of carbon times the Avogadro number. So it's 2 by 5 times 6.022 into 10 to the power 23. It approximately would come out as 2.4 times 10 to the power 23. So in the first question, this corresponds to option D. So in the first question, our answer is option D. Now let's move on to the second question. In this question, you need to identify which of the following molecular formulas are also empirical formulas. Okay. In this question, our basic concept is that in any empirical formula, the coefficient of the atoms of these molecules would be at the simplest ratio. That means you can't reduce the ratio further. In the first option, the ratio comes out to be as 2:6:1. And we can't reduce this further. So this is an empirical formula. Okay. In the second one, you can see that the ratio comes out to be as 2:4:2. Now I can reduce this ratio. I can divide all of these numbers by 2 and I can get 1:2:1. So the second one is not an empirical formula. And the third one, the ratio comes out to be as 5:12, and this is again in the simplest whole number. So option 1 and 3, these are the two empirical formulas, and it corresponds to option B. So in question 2, option B is the correct answer. Now let's move on to question 3. In this question, there is a slightly difficult question. Okay, so in this question, you can see that you need to calculate the volume of ethane gas that will produce 40 centimeter cube of carbon dioxide gas when mixed with 140 centimeter cube of oxygen gas. Okay. So firstly, to solve this question, we need to know the analogy that we can directly convert volume to moles. Okay. So I can write that I have 40 moles of CO2 and I have 140 moles of O2. Okay, so we are basically just converting 1 centimeter cube to 1 mole. That's the first step. Secondly, now we need to find out if oxygen is the limiting reagent or if oxygen is the excess reagent. Okay, So from the stoichiometry of oxygen and carbon dioxide, we can see that like I can write this statement: 7 moles of O2 would give you 4 moles of CO2. Now 1 mole of O2, if I divide both sides by 7, it will give you 4 by 7 moles of CO2. Now I have 140 moles of O2. So 140. This will again give you 4 by 7 times 140. That is equal to 80 moles of CO2. But in this question, we know that we just have 40 moles of CO2. So O2 is an excess reagent. While our ethane would be our limiting reagent. Now, as we know that the ethane is the limiting reagent, we can just use our basic formulation to calculate it. We know that 40 moles of CO2 is produced. So from the stoichiometry of ethane and CO2 now, we know that 4 moles of CO2 is produced from 2 moles of C2H6. Now I can say that 1 mole of CO2 is produced by half mole of C2H6. Like you're just dividing both sides by 4, and finally I can say that 40 moles of CO2 is produced by 20 moles of C2H6. So we know that 20 moles of C2H6 is required. Now, as we know that 20 moles, as I have taken this assumption that 1 mole is 1 centimeter cube, therefore 20 centimeter cube of C2H6 was required in this reaction. So 20 centimeter cube means option B. So option B is our correct answer. Now let's move on to question 4. In this question, you are given a graph that shows the percentage abundance and on the y-axis and the mass to charge ratio on the x-axis, and you need to calculate the relative atomic mass of this element. So for these questions we have already discussed. There is a very simple formula, that is your relative atomic mass is summation of mass times percentage abundance divided by 100. So what does this mean? You need to multiply each of these masses with their percentage abundance and add them together. Okay, so I can basically write AR equals, so first the mass is 24, and you can see the percentage of abundance is nearly 80, so I can just assume it to be 80. Okay, next the mass is 25, and you can see the percentage abundance is midway between 0 to 20, so it's approximately 10. And finally, even for the last one, your mass is 26, and again it's somewhere around 10, so I can just take it as 10, and I would divide it by 100. So upon using our calculator, we would get that the AR, or the relative atomic mass, comes out to be as 24.3 grams. Okay, that is option B. So in this question, our answer is option B. So let's move on to question 5. In this question, we need to identify which element is in group 13. It's again a fairly simple question. To solve this question, let's just pick up any element that's in group 13. Let's say aluminium. Okay, aluminium has 3 valence electrons. Okay, so after losing 3 valence electron, aluminium attains a noble gas configuration. So we know that removing an electron from a noble gas configuration is very difficult. So we should look for, in each of these options, we should look for in which option there is the highest jump between the third ionization energy and the fourth ionization energy. And obviously that's in option B. You see that there is approximately around 8,000 plus jump in the energy. So option B is the correct answer to question 5. Now let's move on to question 6. In this question, you need to identify the correct trend on going down on group 1 and 17. Okay, so specifically you should go down group 1 and group 17. Okay, so our four options are melting points and boiling point, increase, decrease, then electronegativity and ionization energy. So always remember melting point, it doesn't depend much on going down the group. Okay, so we wouldn't consider these two in our answers. So now electronegativity and ionization energy. Firstly, you know that as we go down a group, electronegativity decreases. For example, if you have fluorine, chlorine, bromine, iodine. Okay, what happens is fluorine is the most electronegative element uh, in the periodic table. Okay, and as you go down, the electronegativity decreases. As we know that iodine is like the lowest electronegative element within the halogens. So electronegativity increase would be wrong, but as we go down the group, what happens is more and more shells gets added to that of the element. So as a result, the distance between the electrons in the outermost shell and that of the nucleus increases. And as a result, the ionization energy, that is the energy to remove the electron from the outermost shell, that decreases. And hence, option D is the correct answer to this question. Now, moving on to the next question. In this question, you have to identify that which oxide will give the lowest solution when lowest pH when dissolved in water. So we have four options. Starting with the first one, P4O10. Okay, when we dissolve P4O10 in water, what we get is basically H3PO4 or phosphoric acid. Okay, to balance this, we will just put 4 here and 6 here. So as it is an acid, its pH would be much less than 7. Its pH is approximately like 3. Okay. Next is SiO2. SiO2 dissolves in water, but there is no reaction. Okay. Again, Al2O3 generally doesn't dissolve in water. Okay. Even if it dissolves, okay, the pH of the solution comes out to somewhere around 7. Somewhere around 5. Okay. 5, yeah. But finally, MgO, when you dissolve MgO in water, what you get is MgOH whole twice. Now, this is a base and its pH would be greater than 7. From all this information, we would know that the first option is correct, as we are getting pH equals 3, which is the lowest pH among all the other options. Now, in this question, we need to identify which of the statements are correct. So there are three statements. So the first statement says zinc is not a transition element, and I believe this is true because whenever we are defining a transition element, so transition element is any of these elements which have an partially filled d orbital. So any element having partially filled d subshell is a transition element. Okay. Now zinc, we know that zinc has a completely filled d subshell. Hence, zinc is not exactly a transition element. Hence, our first option is correct. Second is ligands. Ligands are Lewis bases. And I believe this is true too because whenever you have a ligand, ligands always have, ligands should at least have one lone pair of electrons. Now this lone pair, it donates this lone pair to the central metal ion. Okay, so at least ligands should have one lone pair. So as ligands are electron donors, we can directly say that ligands are Lewis bases. This is also true. The magnesium chloride is paramagnetic. That is the third statement. To check this, just write the electronic configuration of central ion. Central ion in this case is Mg2+. The electronic configuration of Mg2+ is 1s2, 2s2, 2p6. We can see that all of the orbitals of Mg2+ are completely filled. There is no orbital that is partially filled. Okay, and as all the orbitals are completely filled, I can safely assume that Mg2 plus is paramagnetic in nature. So all of the three options are correct, and option D is the correct answer to this question. Now in this question, you need to identify that which of these species contains the shortest carbon to oxygen bond length. Okay. Now again, to solve this question, what we need to do is we need to draw the structures of each of the given compounds. So this is the first one, this is the second one, this is the third one, this is the fourth one. We know that double bonds, okay, are stronger than single bonds. So obviously double bonds length would be shorter than that of single bonds. So our first two options can be neglected from this fact. Okay. Now in these two options, check option C. In option C, we have an extra negative charge on an oxygen. This negative charge is actually in conjugation with this double bond. Okay. So what happens is we have this we have a resonance stabilized structure. Okay, so these two bonds, this bond is not exactly a double bond, this bond is not exactly a single bond. Both of the bonds are somewhere in between a double bond and a single bond due to this conjugation. But in the last compound, we see that this bond, there is no conjugation here. Okay, so this bond is definitely a double bond and this is definitely a single bond. So as it is a definite double bond, so I can say that this bond length would be the shortest. So option D is the correct answer. Now let's move on to question 10. And in this question, we need to find out which of the given molecules is the most polar molecule. Okay. So firstly, we know that CF4 and CCl4, these two are non-polar compounds. So these can never be the answer. Why are they non-polar? Because there is a symmetric distribution of fluorine and chlorine molecules around carbon in these two molecules. And as a result, the dipole moments due to this fluorine and chlorine will get cancelled out. And hence this molecule would be non-polar in nature. Now let's draw the structures of the first of option A and option C. Now as both of them are sp3 hybridized, so our structure would be like this, would be tetrahedral, the shape. Here what will happen is we need to identify the dipole moments. So obviously fluorine is more electronegative than carbon, so dipole moments would be directed in this direction, but carbon is more electronegative than hydrogen, so dipole moment would be directed in this way. So there is a complete net dipole moment in the downward side. In the next compound, we see that obviously fluorine is more electronegative than carbon, but chlorine is also more negative than carbon. As a result, some of the dipole moments of these fluorines would be cancelled by this chlorine. Okay, so as a result, I can safely assume that the dipole moment of this compound is much more than this compound, right? So, and that's the reason why option A is the correct answer. Okay, that's the reason why CHF3 is more polar than CClF3. Now, moving on to question 11. In this question, we need to find out the electron geometry around Br in BrF4- and also the molecular geometry. So for this question, we need to firstly find out the hybridization of Br in BrF4-. For hybridization, we have already discussed a trick, and we would be using this one. So firstly, we calculate the total number of valence electron on the central atom, that is Br. And we know that bromine, as it's a halogen, it has 7 valence electrons. So 7. Now we would add any negative charge that is present on this compound, and we have -1 charge. We would subtract any positive charge in this compound, and there is no positive charge here. And finally, we would add all the monovalent atoms attached to the central atom. And here we can see that we have 4 fluorine atoms attached to the central atom. So it would be +4. So here we get the answer as 6. Z equals 6 means we would have sp3d2 hybridization. This is the hybridization. As we have sp3d2 hybridization, we can check the chart and we would know that the electron geometry would be octahedral. So first part, the electron geometry is octahedral. So option A or option C, any one of these two would be correct. Now let's check for the molecular geometry. Now let's check for the total valence electrons on Br. I mean the total lone pair on Br. Total lone pair would be Z minus the surrounding atoms. So Z minus 4, that is Z is 6 minus 4, that is 2. So the main structure, the compound actually looks something like this. We would place the 4 fluorine atoms at the axial positions and both of the electron pairs would be present at the equatorial position. So this thing corresponds to a squared planar molecular geometry. So from these two information, octahedral and square planar, we can say option C is the correct answer to this question. Now in question 12, the metallic bond strength. Now in this question, we have to identify like which of the following elements will form the metallic bond strength from strongest to weakest. To solve this question, we should know how to exactly compare metallic bond strength. Now metallic bond strength completely depends on the charge density. Okay, charge density of ion. Okay, charge density is basically charge by total volume of the ion. Okay, now see here, Mg has only +2 charge. Rest Na, potassium or rubidium, all of them have a +1 charge in their ionic state because these three elements belong to group 1 and Mg belongs to group. Now now in these three, Na has the smallest size. Okay, then comes potassium, then comes rubidium. But Mg has the smallest size. Mg is even smaller than Na. Okay, so Mg, the volume of Mg is the smallest, then comes sodium, then potassium, then rubidium. So I can just assume, I can just from this information I can say that charge density of magnesium is more than that of sodium, and sodium is more than that of potassium, and potassium is more than that of rubidium. So finally it's Mg greater than Na, greater than potassium, greater than rubidium. So option D is the correct answer to this question. Now moving on to question 13. In this question, we need to identify which statement is correct. So there are a lot of statements. So let's read each one of them. O3 bond dissociation occurs at longer wavelength of light than O2 bond dissociation. O3 bond dissociation occurs at higher energy than O2 bond dissociation. O3 bond lengths are shorter than O2 bond lengths, and O3 bond dissociation occurs at a higher frequency of light than O2 bond dissociation. Firstly, let's draw the structures of O3 and O2. O3 is basically the structure. Okay, so mainly the structure is something like this. Okay, while O2 just has a double bond between oxygen. But this bond between O and O in O3 is not exactly a double bond. It is somewhere in between a single and double bond. Okay, it's a hybrid bond. So as double bonds are stronger than single bonds, obviously bonds in O3 are weaker than that of O2. Okay, so bond strength, or I would just write as Bs of O3 is less than that of Bs of O2. Okay, so as bond strength of O3 is less than that of O2, that means we would require lesser energy for bond dissociation of O3 than as compared to O2. But option 2 says bond dissociation occurs at higher energy than O2 bond dissociation. So this is wrong. Nextly, bond length. Bond length is inversely proportional to bond strength. Okay, so bond length is inversely proportional to bond strength. So I can say that bond strength of O2, bond length of O2 is less than that of bond length of O3. Okay, we are just doing the inverse of both of them. So here this option says bond lengths are O3 bond lengths are shorter than that of O2 bond lengths, but we just here analyze that bond length of O2 is shorter than that of O3. Option C is also not correct. Now energy, we know that O2 needs more energy for dissociation. Okay, and for energy of light, the formula is HF for a photon. Okay, higher the frequency of photon, higher is the energy. The option D says the bond dissociation of O3 occurs at a higher frequency than that of light. But we know that we need lesser energy for bond dissociation for O3 as compared to O2. So Obviously, O2 would require a photon with higher energy as compared to O3. So option D is also incorrect. Now we know that E equals HF, that is also equal to Hc by lambda. So energy is inversely proportional to wavelength. Here option A says bond dissociation occurs at a longer wavelength of light than O2 bond dissociation. Now obviously O3 requires lesser energy. So as energy is lesser and energy and wavelength are inversely proportional, so obviously we would require a photon of longer wavelength as compared to O2 for O3 bond dissociation. So option A is correct in this case. Now moving on to question 14. In this question, it is a fairly simple question. We need to find out the equation which shows the enthalpy of formation of ethanol. There's some prerequisite knowledge that is required to solve this question, that ethanol is generally formed in liquid state. Okay, but in this first A and B, in these two options, ethanol is formed in gaseous phase. So A and B are ruled out in this way. Now for enthalpy of formation, the main rule is whenever we are defining enthalpy of formation, we are looking for the change of enthalpy for the production of 1 mole of product. In both these cases, you can see that only 1 mole is formed in option C, not in option D. So option C is the correct answer. So hence the enthalpy change of option C is basically the enthalpy of formation of ethanol. Now in this question, we need to find out the relative bond strength. I mean, which the products are reacting, which one has a greater bond strength, and also which one has a greater magnitude of activation energy. So firstly, first things first, we should know that delta H is basically summation of bond enthalpy of reactants minus summation of bond enthalpy of products. Obviously, as delta H is negative, we can say that the negative part is greater than that of the positive part. So relative bond strength of products is greater than that of relative bond strength of reactants. So either option B or option C can be correct. Now let's check for the next one, that is the relative magnitude of activation energy. Now for these questions, we can draw the activation energy curve easily. Let's say this is the reactant part. Let's say R is your reactant. Let's say this is the curve, this is the energy profile, and this P is the product. So for the forward direction, check that this is the activation energy EA. Okay, but for the reverse reaction, your activation energy would be EA plus this delta H of this reaction. So the forward reaction is EA, backward reaction is EA plus delta H. So obviously magnitude of activation energy of the reverse reaction is greater than that of the forward reaction. So from this information, we can say that option B is the correct answer. Now for question 16, we need to find out the standard hydration enthalpy of sodium Na plus ion. Okay, so here basically we need to know the steps. So whenever we are producing a solution of delta H naught solution of NaCl, what are the following steps? Firstly, we are mixing NaCl in water. So what happens first? Firstly, the 3D structure of NaCl gets destroyed. Okay, so the first energy change is delta H naught lattice of NaCl. As the structure is broken, we get the Na plus and Cl minus. The next step is this Na plus and Cl minus ions, they get dissolved in water. So we would write the delta H naught hydration of Cl minus plus delta H naught hydration of Na plus. So this is our final equation, and we can just plug in the values to get the answer. So delta H naught solution is plus 4 is equal to lattice is plus 790, hydration is minus 359, plus this is delta H naught hydration of NaCl. Let's just write it as delta H naught. So delta H naught is equal to plus 4 plus 359 minus 790. So from the options, option B is the correct answer to this question. Now moving on to the next question. This question we need to know that in which reaction becomes more spontaneous as temperature increases. Basically, we need to find out any of this reaction in case, I mean in the case that delta S, or the entropy, increases. Okay, entropy increases when the reactants are getting converted to products. Let's start from the first one. See, you have a solid as a reactant, and at the product, you have one solid and one gas. As a result, what happens? The randomness of the system has increased. Okay, so delta S is greater than 0 in the first case. Second case, see, you have 4 gaseous moles on the reactant side and 2 gaseous moles on the product side. As a result, what happens? Delta S, or the entropy, has decreased. The randomness of the system has increased. Similarly, in option C, you have 7 gaseous moles on the reactant side and only 6 gaseous moles on the product side. So delta S is again less than 0, negative. Finally, in the last case, you see you have a gas and a liquid on the reactant side, and on the product side, you just have a liquid. So what happens is your randomness has decreased. Okay, you're just getting one liquid from a gas and a liquid. So delta S is again less than 0. So analyzing all the options, as option A is the only one having delta S greater than 0, so option A is the correct answer. Now in question 18, you need to, in this question, they're asking which of the apparatus can be used to monitor the rate of this reaction. Okay. Now they have given us 3 options. One is a pH meter, another is a gas syringe, last is a colorimeter. So in this reaction, as H plus ions are getting produced, what happens? The pH of the solution will keep on decreasing. The solution will become acidic. Okay. So obviously we can use pH meter to get the rate of this reaction, okay, as the pH will tell you the concentration of H plus ions. Second option is gas syringe. Now gas syringe is basically used whenever you have gaseous reactants or products. In this case, we just have aqueous reactants and products, so gas syringe cannot be used. Last is colorimeter. Now colorimeter basically is an instrument which calculates the wavelengths of light that has been absorbed by the solution. Now obviously, as a reactant and product, both are different. What happens? Well, reactant will absorb a specific set of wavelengths, while the products will absorb a specific set of wavelengths. So obviously colorimeter would be able to tell us the change or the shift in this wavelength. So obviously colorimeter can be another option. So 1 and 3, so option B is the correct answer to this question. Now question 19 is like kind of an informative question, but it's okay, we can solve it very easily. So in this question we need to answer that which change does not increase the rate of reaction. Now we all know that increase in temperature will obviously increase the rate of any reaction, okay, because the rate constant will increase. Increasing the concentration of H2SO4, increasing the reactant concentration, will also increase the rate of this reaction. And also, if we increase the particle size of CuCO3, it will also again result in the increase of this rate of reaction. So just that stirring the reaction mixture will not cause any change in the rate of reaction. Rate of reaction can only be caused if you have a chemical change, okay, or rather, like if you have a bigger particle size of CuCO3, then also it would work. Now question 20, this is the last question for this video, and we will be continuing the rest from 21 to 40 in the next video. So let's start with this question. Now we should know the dimension of rate. Dimension of rate is basically mole per dm cube times second, okay, and the dimension of A and B is equal to this concentration, that is mole per decimeter cube, and we need to find out the dimension of K. Okay, so basically if we just write it here, mole per dm cube per second is equal to K times mole per dm cube, this is for A, times mole per dm cube, this is for dm cube whole square, this is for B. So upon cancelling and writing, what we get is dm to the power 6 divided by mole squared and second. So the dimension of K is basically dm6 mole to the power minus 2 s to the power minus 1. So option C is the correct answer to question 20. So with this, we are done with the first 20 questions, and hope you enjoyed the video. Don't forget to like, share and subscribe to our channel.